Hello there, everybody. I hope you are doing just magnificently on this fine day. I know I certainly am. So I thought I'd take the time to show you how to balance a redox equation in acidic solution. So the next video after this is going to be basic solution, but for this video, we're going to balance a redox, that's oxidation reduction. Reduction, of course, being the gaining of electrons, oxidation, of course, being the loss of electrons. We're going to balance this equation under the assumption that it's taking place in acidic solution. So here's the equation. We have BrO3 minus, that's the bromate ion, plus N2H4, that's called hydrazine, reacting to produce the bromide ion, Br minus, and some nitrogen gas. So clearly, this equation is not balanced as it's written. That should be pretty obvious. We have oxygen and hydrogen over here on the left. We have neither oxygen nor hydrogen over here on the right, so we have to balance this equation. Now, luckily for us, there is a 7-step series of steps that we can use to balance this equation. Now, you might be thinking 7 steps, that's a lot, and perhaps it is, but as with anything, practice makes perfect. You practice over and over and over again. The 7 steps will become second nature to you. You certainly don't want to be doing this for the first time on test day, so make sure you practice, practice, practice. Okay, so let's go ahead and go about balancing this equation. So the first step is to assign oxidation states to every single atom in this chemical equation and identify what is being oxidized and what is being reduced. Now, if you're looking for a from the bottom up type of lesson on assigning oxidation states, you're not going to find it here. This video we're kind of doing this under the assumption that you more or less already know how to do that. I'm going to go through it briefly, but if you want a more comprehensive lesson on that, I do have a 2-part video series on redox reactions in which we learn from the bottom up what an oxidation state is and how to assign oxidation states. So let's go through it briefly. So starting with the bromine atom over here on the left-hand side of the equation, well, there's the bromine. You know what? I'm not even going to start with that. I'm going to start with the easy ones. I've changed my mind. So the easiest one, the easiest element here, or atom, to figure out what its oxidation state is going to be this nitrogen over here, which is going to be 0. And the reason why it's 0 is because the oxidation state of any free element, any free atom or group of atoms, is going to be 0. So that's pretty easy. The next easiest one is going to be this one over here, the bromine atom. The oxidation state of this bromine atom is going to be -1. And the reason why is because any monoatomic ion, any element that's in a monoatomic ion, the oxidation state of that element will be the charge of the monoatomic ion. So these two are the easy ones. Over here, it's a little bit more difficult. If we go with the bromate ion, we need to figure out the oxidation state of bromine and of oxygen. And there's a couple of rules that are going to come into play here. One is that the sum of the oxidation states of bromine and of oxygen are going to be equal to -1. Now, the reason why the sum of, and I'll go ahead and write this out, so I'll just say OX Br plus 3 times the OX of oxygen is equal to -1. The sum of the individual oxidation states of all the atoms in this formula is going to be equal to the charge of the polyatomic ion, which in this case is -1. So the oxidation, so I'll just say it one more time. The oxidation state of the bromine plus 3 times the oxidation state of the oxygen is going to be equal to -1, the overall charge of the polyatomic ion. Now, generally, unless otherwise specified or under special circumstances, the oxidation state of oxygen is almost always going to be -2. So this is an equation in which we have one unknown, right? So we can solve for the unknown in this case. So we have the oxidation state of bromine plus 3 times -2 is equal to -1. 3 times -2, that's simply going to be -6. So we have the oxidation state of bromine -6. Go ahead and make that a little cleaner for you. The oxidation state of bromine -6 is going to be equal to -1. And so by simply adding 6 to both sides of this equation, we get that the oxidation state of bromine is +5. And as we previously established, the oxidation state of oxygen is -2. So So we just figured that one out. Let's move on to the hydrazine, right? So for the hydrazine, excuse me, we know that the sum of the oxidation states of all atoms in this is going to be equal to 0, which is the overall charge. This is a neutral compound with no charge. So we know that 2 times the oxidation state of nitrogen plus 4 times the oxidation state. I'm going to go ahead and do that again to give myself a little bit more room. Excuse me here. Just do it all over again. So 2 times the oxidation state of nitrogen plus 4 times the oxidation state of hydrogen is going to be equal to 0. And it's another one of those rules, like earlier we said that unless otherwise specified, oxygen has a -2 oxidation state. It's a similar rule for hydrogen, except it's going to be +1. And like I said, if you watch my 2-part video series on redox reactions, it makes it clear. It's a little bit less confusing. Hopefully you're not learning about redox for the very first time in this video. If you are, I apologize if it seems a little confusing, but I would definitely recommend watching those 2 videos. Anyway, so the oxidation state of hydrogen is almost always going to be +1. So if we sort of plug that into this equation here, we know that, right, it's going to be 4 times the oxidation state of hydrogen, which is +1, right? So we know that twice the oxidation state of nitrogen plus 4 is equal to 0. If we subtract both sides of this equation by 4, just algebraically, we'll get that twice the oxidation state of nitrogen is equal to -4. And then finally, if we divide both sides of this equation by 2, we'll get the oxidation state of nitrogen is equal to -2, because -4 divided by 2 is equal to -2, right? So step 1 is pretty much almost done. We've successfully assigned oxidation states to every atom in this equation. And so the next step, or the next sub-step, if you will, in step 1 is to identify which substances are getting oxidized and which substances are getting reduced. Now, remember that oxidation is the loss of electrons. So that means that the oxidation state will become more positive in the case of oxidation. So of these species, well, we don't really know for oxygen, we don't really know for hydrogen because there's no hydrogen over on the right. So really we're looking at bromine and nitrogen. So of those 2 elements, bromine and nitrogen, which one's being oxidized? I'll give you a second to figure that out. Okay, I think it's been a second. So clearly the nitrogen is being oxidized because it's clearly losing electrons, right? Because it's going from an oxidation state of -2 to an oxidation state of 0, right? And then bromine, it's sort of the inverse, right? It's going from an oxidation state of +5 to an oxidation state of -1. And so bromine is gaining electrons. Bromine is being reduced. So step 1 is complete. We've assigned oxidation states. We know what's being oxidized. We know what's being reduced. Good job for us. The second step, step 2, is to separate the chemical equation into 2 half reactions, one for oxidation and one for reduction. So I'll go ahead and label them, one for oxidation and one for reduction. So as we established a moment ago, the nitrogen is being oxidized. So the nitrogen containing species, this hydrazine here, I'm having a hard time saying that, is the stuff that's going to undergo oxidation. So let's put in that chemical formula for hydrazine. That's N2H4. Now, for the purposes of speed and just to make this reaction or this process a little bit cleaner, I'm going to ignore these little states of matter, the aqueous, the gas, and all that stuff. I'm going to omit those from here on out. Maybe I'll sort of pop them in at the end to make it nice and proper, but I think it'll just be cleaner and easier to just ignore those for the time being. So just imagine that they're coming along for the ride, so to speak. So we have the hydrazine reacting to form the nitrogen N2. So that's our oxidation half reaction, half equation, right? And then for reduction, that's going to start with the bromate ion. So I'll go ahead and put in that bromate ion, BrO3 minus, and that's going to react to form the bromide ion, Br minus, right? So we have successfully split it up into half reactions, and step 2 is done. Now step 3 is sort of composed or comprised of 3 sub-steps. So for step 3, we're going to balance each of these half reactions with respect to mass. And there are, like I said, there are 3 sub-steps that must be completed in the following order. The first is to balance all elements other than hydrogen and oxygen. Once those are balanced, we're going to balance oxygen by adding water. And then after that step, we're going to balance hydrogen by adding H+. So if we turn our attention to the first of those 3 sub-steps, we're going to balance all elements other than hydrogen and oxygen. And in this case, for this particular problem, it won't always be this easy, but leaving the coefficients in front of these as understood ones satisfies this step, right? So in the oxidation half reaction, we have 2 nitrogens here, we have 2 nitrogens here, nitrogen is already balanced. Similarly, for the reduction half reaction, we have 1 bromine over here, 1 bromine over there. So everything except for hydrogen and oxygen is balanced, right? So that step is done. So the next part in that 3-part series of steps that compose step 3, we're going to balance oxygen by adding water. As you can see in the oxidation half reaction, there's no need to do that because there's no oxygen, so we don't have to balance oxygen up here. But in the reduction half reaction, we have to balance oxygen by adding water because we have oxygen over here on the left-hand side of this half reaction, right? So we're going to add enough water to balance oxygen. So we're going to add some water, just add water. So then the question becomes, how many water molecules do we need to add, or how many moles of water do we need to add to balance with the existing 3 oxygens over here on the left? And the answer obviously would be 3, right? If we take that coefficient of 3, multiply it by the understood coefficient of 1 on the water, we'll get 3 oxygens on the right, balancing with that 3 oxygens on the left. So we're good to go. So the last and final sub-step in step 3 is to balance hydrogen by adding H+, right? So in the oxidation half reaction, we see that we have 4 hydrogens on the left, so we need 4 hydrogens on the right, and so we're simply going to add 4 H+ on the right. So hydrogen is now balanced in the oxidation half reaction. And then since a moment ago we added hydrogen to the right-hand side of this reduction half reaction by adding water, we need to add enough H+ to balance out with the hydrogens. How many H+ do we need to add? Well, how many hydrogens do we have on the right-hand side? Well, we have 3, that's the coefficient, times 2, the subscript next to that hydrogen, for a total of 6 hydrogens, and so we need to add 6 H+, right? So step 3 is now finished. We can move on. Now step 4 is to balance each half reaction with respect to charge by adding electrons. And we need to understand that the sum of the charges on both sides of the equation should be made equal by adding as many electrons as necessary. So what does that mean? Well, if we take a look at our oxidation half reaction, right? What's the charge on the left-hand side? What's the charge on the right-hand side? Well, on the left-hand side, our charge is 0 because we just have this neutral molecule here with 0 charge. And then on the right-hand side, our charge is going to be 4+ because we have 4 of these hydrogen ions, each with a charge of +1. And so we need to add enough electrons to the right-hand side of this equation here to result in a 0 charge, which would match the left-hand side of the equation. So that's going to be 4 electrons, right? And the reduction half reaction is a little bit more tricky. I think it would be worthwhile for us to identify the charge of both sides of this equation first. So we have 6 H+ over here, so that's 6+ coming from this species here. We have 1- coming from this species here. So 6+, 1-. Overall, that's going to be 5+ in the reactants on the left-hand side, right? And then on the right, we have the 1 minus coming from the bromide ion here, so, and then the water molecule contributes nothing to the charge because it's neutral. So we have 1 plus over here and 5 plus over here. Excuse me, I said 1 plus, I meant 1 minus. Made a little bit of a mistake there, so bear with me. For those of you who spotted it, kudos to you. So the idea here over on this, with this reduction half reaction is that we need to add enough electrons to the left-hand side of this equation to get an overall charge that matches the charge of the right-hand side of the half reaction. The right-hand side of the reaction is 1 minus. We need to add enough electrons to go from 5 plus to 1 minus. So in other words, it's like 5 plus what equals minus 1, right? You can think of it like that. 5 plus what number of electrons is going to be minus 1. And so in this case, that's going to be 6 electrons. And I think, looks like I'm running out of a little room, so I'll just pop it in here at the bottom. 6 electrons. Okay, so hopefully that makes sense. Sorry, I dropped my I have a little cheat sheet off screen that I'm working with here. Dropped it, so I had to pick it up. Okay, so we have these two half reactions that have been balanced not only with respect to mass, but also with respect to charge. So step 4 is done. Step 5 is to make the number of electrons in both half reactions equal by multiplying one or both of the half reactions by a small whole number. So as they're currently written, the number of electrons in these half reactions are not equal, right? We have 4 electrons over here in the oxidation half reaction. We have 6 electrons over here in the reduction half reaction. So again, we need to figure out how to make those number of electrons equal by multiplying one or both of these equations by a small whole number. Now it looks to me like we're not going to get away with multiplying just one of the equations by a small whole number, right? You know, because if we multiply this equation by a factor of 2, let's say, we'll end up with 8 electrons, which is more than 6. So we're going to have to multiply both of these equations by a factor. And so when you're trying to figure out which factor by which to multiply both of these equations, well, it's basically like a least common multiple sort of thing, right? So we want the number of electrons, when it's all said and done, we want the number of electrons to be the lowest number that is divisible by both 6 and 4. So we want the lowest number of electrons that 4 and 6 can both cleanly divide into, right? And that number is going to be 12 electrons. So since we've sort of found that least common multiple, well, what factor do we need to multiply each of these equations by to get us 12 electrons? Well, in the case of the oxidation half reaction, that number is going to be 3, right? 3 times 4 electrons is going to be equal to 12 electrons. And for the reduction half reaction, we have 6 electrons. So what factor do we need to multiply 6 by to get to 12? That would be, of course, 2. So since we're multiplying each of these half reactions by these factors, we need to distribute that coefficient through and multiply everything in this equation by that coefficient, right? So if we do that with regard to the oxidation half reaction, we're going to get 3 of these hydrazines, because the coefficient was 1, now it's 3, right? And we're going to end up with 3 of the nitrogens. We're going to multiply 3 by the 4 H pluses, so that's going to become 12 H pluses. 3 times the existing 4 is equal to 12 H pluses, and then the same thing with the electrons. We had 4, we're multiplying it by 3, so that becomes 12 electrons, right? And we're going to do the same approach with the reduction half reaction. We're going to multiply everything in that equation by the factor of 2. So the 6 H pluses, we'll multiply that by 2, that'll become 12. The bromate ion, we're going to multiply that 2, that'll become 2 bromate ions. The 6 electrons, we'll multiply that by 2, that'll become 12 electrons. the bromide ion, we're going to multiply this understood 1 by 2. That'll become 2 bromide ions. And then finally, with the waters, we had 3 waters before. We're going to multiply that by 2, and that's going to become 6 waters. So we're almost done. We've completed steps 1 through 5. Now we're going to move on to step 6, which is to simply add the 2 half reactions together, canceling out electrons or other species as necessary. So if we add these 2 equations together, we're going to see some things canceling, right? The 12 electrons on the left are going to cancel out with the 12 electrons on the right. The 12 H pluses on the left are going to cancel out with the 12 H pluses on the right. And everything else remaining is going to be a part of that combined chemical equation. So I'm trying to figure out the easiest sort of way to do this. Let's see. I think I can just, I'll just remember that I have my 3 nitrogens over here, 3 N2s, and then I'll add sort of everything else. You don't really need those anymore, right? So I have my 3 N2H4s plus my 2 bromate ions, 2 BrO3 minuses, reacting to produce my 2 bromide ions, excuse me, plus my 6 waters, and then my 3 nitrogens, right? 3 diatomic N2s. So this is the combined equation. Upon adding those 2 half reactions together and canceling both the electrons and the H pluses. And then the final step, step 7, is to verify that the reaction is balanced, both with respect to mass and with respect to charge, right? So if we set ourselves up a little table here with all of the elements, we have nitrogen, we have hydrogen, we have bromine, we have oxygen, and we have charge, right? And we have the reactants, we have the products. So we need to make sure that the number of atoms of each element is the same on both sides, and that the charge balances also. So let's go ahead and just go through that briefly. So we have in the case of nitrogen, we have 3 nitrogens times 2, or the coefficient of 3 times 2 nitrogens rather, 6 nitrogens on the left. How many nitrogens do we have on the right? Well, 3 over here times 2, 6 nitrogens, so nitrogen is balanced. In the case of hydrogen, we have the coefficient of 3 times the 4 hydrogens over here, 12 hydrogens. Do we have 12 hydrogens on the right? Looks like we do. 6 times 2 is 12 hydrogens. So that balances just fine. Moving on to bromine, now we have 2 times 1, which is 2 bromines on the left, 2 times 1, which is 2 bromines on the right. Oxygen, we have 2 times 3, or 6 oxygens on the left, and we have 6 times the understood 1, which is 6 oxygens on the right. And when it comes to charge, well, we have an ion with a charge of 1 minus times this 2, so that's 2 minus on the left, and the same is true on the right. And we have an anion with a charge of 1 minus times 2, so 2 minus. So everything in this equation is balanced, and if you wanted to be super proper and correct about it, I don't know how anal your teacher is, but you would add in the states of matter. Hydrogen is a gas, bromate ion is aqueous, bromide ion also aqueous, water, that's a liquid, and then nitrogen is a gas. And I only popped them in at the bottom because I didn't leave myself enough room to write them in. So I hope you found this video helpful. We now have a balanced redox equation in acidic solution. The next video is going to be balancing a redox reaction in basic solution, which is the steps are pretty similar, but there's a little bit of extra stuff you have to do with basic solution that you don't have to do in acidic solution, but we'll explain that in the following video. Thank you very much for watching. If you found this video helpful, I would certainly appreciate leaving a nice thumbs up on it. And if you're not subscribed, my recent study of my analytics has shown me that roughly 95% of the people who watch my content are not subscribed. I would like that number to be lower and the number of people subscribed to be higher. So please consider subscribing if you haven't already done so. And if you do subscribe, I would wholeheartedly appreciate you clicking that notification bell, choosing all notifications. That way you'll be notified the instant my next educational video is uploaded. Thanks again, and stay tuned for the next video. All right, take care.